Hello Internet, welcome to another electromagnetic field theory tutorial. In this tutorial we are going to understand Helmholtz equation and then we'll study the expressions for alpha, beta and gamma. Now before we derive Helmholtz equation and understand the significance, I'd like to mention that it requires a thorough understanding of wave equations in lossy media. Now we know that the generalized form of wave equation for lossy media is, I'll take up the case for E vector. It is given as this. Now again, needless to mention, the left hand side signifies the spatial change, the right hand side signifies the time change, and in the right hand side you'll find a term with sigma that represents the conductivity of the medium. So lossy media will have a very huge value of sigma. So but we simply need this equation as the base equation to derive Helmholtz equation and then further derive alpha, beta, which are attenuation constant and phase constant. Now what happens is, if a wave is traveling in certain direction, the basic nature of any propagation of electromagnetic wave is that it is most likely to be in sinusoidal in nature, and there are two properties associated with the propagation of these kind of waves. The first one being its sinusoidal nature. Its sinusoidal nature is expressed by a term known as the phase constant. Phase constant tells you how quickly the wave is changing the phase, and it is measured over a period of a full wave. For example, if I were to compare these two waves, I would say the second wave is changing its phase more quickly than the first wave, because the first wave is taking this much time to cover an angle of 360 degrees. However, the second wave is taking a lot less time to cover the same amount of angle in degrees as compared to the first wave. So we would say that beta of wave 2 is greater than beta of wave 1. Now the basic understanding of phase constant tells you that any wave with a higher beta would likely to be of a higher frequency. Any sinusoidal wave will have that characteristic for sure. And the second characteristic of any real life propagation would be the dying out of the wave. We cannot expect the wave to go on forever. because the waves are traveling in certain medium that has certain impedance. For example, if you subject a wave to free space, free space has got an internal impedance of 377 ohms. So this much amount of resistance is being offered to a propagating wave. So the wave is bound to eventually die at some point in time. But how quickly the wave is going to die is dependent upon a factor which is known as alpha, which is known as attenuation factor. Beta is known as phase constant. And in wave equations terminology, both these quantities are represented by a complex number gamma, which is a combination of these two parameters, where alpha is the real part and beta is the imaginary part. Alpha represents attenuation constant and beta represents phase constant. So wave equations are going to tell us two very fundamental characteristics of a wave. The first one being alpha, that is to how quickly this is going to die out, and the second one is beta, how quickly it is changing its phase from 0 to 90 degrees to 180 to 270 to 360. And in order to derive mathematical expressions for alpha and beta for any wave equation, we take help of Helmholtz equation. So it is essential to derive Helmholtz equation first and then extract alpha and beta from that Helmholtz equation. Now, Helmholtz equation assumes that the waves that we are talking about are sinusoidal in nature. So for sinusoidal waves, the time rate change is substituted by j omega, where omega is the angular velocity. So omega is that one thing that introduces the component for a sinusoidal propagation. The angular velocity is that component. So when we substitute this in our characteristic wave equation for any medium or lossy medium, what we get is Laplacian E mu sigma j omega E plus mu epsilon j square omega square E, and a little bit of rearrangement gives us j omega mu as a common term, and then sigma plus j omega epsilon multiplied by E. Now this term here with the vector E on the right hand side is a little too cumbersome to understand, and it does not straight away gives us the desired values for alpha and beta. So what Helmholtz proposed that this term be substituted by gamma square E. So now the wave equation has taken up a very compact format. Any wave equation in its most generalized form can be represented by Laplacian of A on the left hand side and gamma square A on the right hand side, where of course gamma is the propagation constant. And we have already discussed about propagation constant as the sum of attenuation constant and phase constant. Any propagation should have these two fundamental properties. So now our job is to find out the value of alpha and beta from this mammoth term. So what we have here is we have gamma square is equal to j omega mu into sigma j omega epsilon, or gamma is equivalent to under root of this huge term. Now extracting real and imaginary parts from this term should give us alpha and beta. So in other words, we have alpha plus j beta is equivalent to this term in the under root. After solving, we get the value of alpha to be equivalent to, I'm just writing this value directly. If you wish, you could solve and separate the real and imaginary parts. The value of alpha will be this one is not under the root. Of course, this one is under the root of this main under root, and similarly beta is everything same, but this minus sign will be substituted or replaced with a positive sign. I don't know why I take this under root way too long. Now I would say you could commit these values to memory, because there's no use extracting these values and separating the real and imaginary parts from this cumbersome term, but we can commit these two things to memory. And then what happens is we need to mention some special cases for alpha and beta. Now for the first case would be for good conductors. Now please understand, if you remember these equations for alpha and beta, and if you get a numerical for good conductors, you will be given the value of sigma. But to make the thing simpler and for better approximation and make the calculations quicker, we use some approximations that you can substitute in these big formulas. The first approximation is this, that for good conductors the value of sigma upon omega epsilon is going to be way too large as compared to 1. And for good dielectrics, the value of sigma upon omega epsilon can be substituted as way less than 1. Now, if you substitute these approximations in the main formulas for alpha and beta, then alpha reduces to a very simple expression and beta still remains a little bulkier as compared to alpha. But you can use these direct shortened formulas to solve numericals for these two values for alpha and beta are for good dielectrics. I'll mention the values for good conductors in a different colored pen, where we so this approximation results in this set of values, and this approximation is going to result in another set of value where alpha and beta are going to be very, very simple. So you just have to remember one equation for alpha and beta. And for good conductors, there's going to be one more parameter, skin depth, which is going to be the reciprocal of alpha. So that becomes now we can use these approximated formulas for alpha, beta and gamma for solving numericals. And I hope this tutorial was helpful, and if you considered this helpful, please consider subscribing to my channel and share the videos for good words. And thank you so much for watching the video. Have a good day, good life. Bye.